The purpose of this lab is to utilize and apply the following key concepts and principles, which are Newton's first law of motion, Newton's second law of motion, the momentum principle, the velocity update, and position update formula as well. Newton's first law says that an object at rest or an object in motion will remain in such state unless acted upon by an external force. Newton's second law states that the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. The momentum principle can be used to determine the net force on the object by analyzing the motion, and lastly, along with the velocity update formula and position update formula, I will use these principles to determine if the following statement is true. Constant velocity is defined as an object moving at the same speed without changing direction, meaning the net force would have to be zero. When I later compare my observed experiment results to the predicted computational model, I will be able to determine if the moving object was in fact at a constant velocity in the designated time. Furthermore, I needed to become more familiar with softwares that gathered the experimental and computational models through Tracker and GlowScript. The circular jewelry box was recorded on a cellular device, and the motion was analyzed via Tracker. And the model was then computed using an online software program called GlowScript that utilizes Python. This lab also utilizes the flat surface to ensure that the gravitational force is balanced with the surface for the duration that the object is in motion. Using Tracker, the object's motion was measured following the center of mass as designated by the red dot, moving along the positive x-axis. The following graphs on the right show the relationship between position and time. The graph is linear, which would demonstrate that the system is moving at a constant velocity. The initial position of the object is located at 5.551 times 10 to the negative 17th meters, and the total change in time is 0.467 seconds, but the time steps are 0.033 seconds, and that was what I used in my calculations. The formula for average velocity is shown here, change in displacement over the change in time. And in this lab, the initial velocity was calculated by the change in position from the first two data points divided by the change in time for that particular duration. The initial velocity came out to be 0.271 meters per second, which I got from subtracting the initial position, 5.551 times 10 to the negative 17 meters, from the second position, 8.935 times 10 to the negative 30 meters, divided by 0.033 seconds minus 0 seconds. We can use this information to utilize the velocity update formula, which can be solved for by dividing the momentum principle by the mass to get final velocity equals initial velocity plus the net force divided by the mass times delta t. As shown, the final velocity was the same as the initial velocity because the net force was 0, which made anything after the addition sign 0. This demonstrates that the object was moving at a constant velocity based off of the observed dataset. We can then take the average velocity and plug it into the position update formula to find the final position. GlowScript was used to determine the predicted measurements of the system. In order to execute the starter code, we needed the mass, the initial position, initial velocity, time steps, time interval, and the net force, which was 0. And since the net force is 0, the final initial velocity are the same, and the program will predict the object's position off of the constant velocity. Furthermore, Newton's second law must be rearranged to be solved for the final velocity, which is shown here. The final position formula also needed to be modified so that the final position is being solved for, and that will allow the use of line 46 to input values of the average velocity into the designated variable called ball.vel. When the code is run, a model graph is displayed which shows the predicted positions where the circular jewelry box is traveling at a constant velocity. The green line in the position versus time graph represents the predicted model computed by GlowScript, and the pink line is the observed data that I collected using Tracker. As shown, the two lines do not perfectly match up, which allowed me to conclude that my system did not travel at a constant velocity, meaning the object was being acted upon by net forces that were not 0. To improve the observed results, a different surface could have been used for the object, one that was much smoother, which would have allowed for the object to travel at a velocity closer to that of being constant or exactly constant. Furthermore, I could have used better time frames to collect my data where the object was not initially speeding up from the initial momentum in the beginning. If the axes were to be flipped, the numerical velocity, or in other words, the absolute value of the velocity, would be the same. The same distance would have been traveled, but the velocity vector would be different because the direction of the object would have been flipped to be in the negative x direction, meaning moving to the left instead of in the positive x direction that the object was traveling in for this lab. Lastly, my position versus time graph would have also had a negative slope. According to Newton's second law, for the velocity to be constant, the net force must be 0. However, in this lab, we cannot determine the exact pushes or pulls on the system that would produce a net force of 0. I did know that there was the force of gravity and normal force pushing up, but there were forces that were not accounted for, such as friction, and so we cannot determine the net force of all the pushes and pulls acting on the system because we don't have the exact numerical values to calculate. In conclusion, My observed data and the predicted data by the computational model differed due to outside forces acting on the object. For example, the force of the push of the ruler by my hand could be a strong factor that played a part in the velocity of the object not being constant. If a system were truly perfect, then there would be no outside forces or interactions acting upon the system, and therefore it would be able to have a zero net force resulting in a constant velocity. Newton's second law is applicable. We just have to consider outside forces acting on a system.